is another video lecture in Math 442. This is section 6.3.3. We're going to apply what we used in the previous video to do a global error analysis on a more general problem. And let's get started. Now to cover section 6.3.3, we're going to do a similar sort of global error analysis, but we're going to apply it to the more general IVP where it is stated as u prime is equal to f of u. So now f is no longer a linear expression of u, it's just some general function that we're thinking about. It's assumed here to be autonomous. So t, the t variable or the independent variable, doesn't appear explicitly on the right-hand side, but f can be a gnarly function of u. You'll find a lot of similarities between this and the previous video. So applying Euler's method, that should look exactly the same as it was before. Nothing new there. I'm going to write down my local truncation error, and this time I'm just going to leave it in this form here. So what you're going to see is that instead of substituting for f like I did before, f is just going to be given as it is here. Now, I won't go through all the details that we saw before, but everything follows the same as in the previous video. My local truncation error at the nth time step is given by 1/2 k times u prime plus order k squared terms. Just as before, I'm going to rewrite this equation so that now it looks like this, because that's the form I'm going to need for the global error. And now I'm going to form that global error expression. I'm going to use this thing right here, and I'm going to use the expression, which is 6.13 on the previous page of the notes. So we come down here and we say the global error at the n plus first time step is given by un plus 1 minus u at tn plus 1. This piece comes from my Euler's method on 6.13, and this piece comes from the above that you see there. And the term that I really want to combine here that's important to me is it's this guy right here, and I recognize that as my global error at the nth time step. And then out here, I have all of my f functions that I have to deal with. I'm going to start as I always start. I'm going to take absolute values. Taking absolute values and applying triangle inequality to everything, we end up right here. And now I can use that expression for a Lipschitz continuity in order to rewrite this in an inequality form as less than or equal to that Lipschitz coefficient times the things that are inside the f, right? That's this, and those two things go here and here. So that helps a lot, because what that means is that in both of these terms, I've got a global error now that I can combine. So these come into like terms. Let me erase some of my mess here. These come into my like terms. The global error at the n plus first time step is less than or equal to a multiplier times the global error at the nth time step, and k times a local truncation error. All right, that's equation 6.15 in your textbook. Once we arrive here, then we want to play the same game we did before and do, I don't know if we really call it inductive or recursive. I'm not sure which is the best phrase here, but what we're going to do is then use what you see in equation 6.15 to recursively express the error at the n plus first time step in terms of the error at the initial time step, and then a sum. This is the error at the initial time step. And then a sum that's going to involve a multiplier and local truncation errors at each step. There's not much I can say to help you get from here to here, except that you have to work those things out on your own. This is recursively applying this same relation that you see in equation 6.15 to lower values of n as you unwrap that global error and how it's related to its previous time steps global error. And there's no substitution for you thinking about it yourself and working on it. So I will leave it there, allow you to process all of these terms. Hopefully you can get to a place where you can get all the way down here at the end to this inequality step. Okay, that is the key to actually unraveling what the global error is in terms of initial condition errors E0 and local truncation errors. All right, so once we get here, the key is to play the same game as before with the inequalities. And this should look very familiar. We did this already, only now we see that we've got a Lipschitz coefficient, capital L, that floats into the situation. For now, just assume that this guy is equal to 0. So assume there's no error in your assignment of your initial condition. Then the global error is simply k times a summation of all of those local truncation errors at each step. I am going to use an inequality here where I have replaced this in each step with its maximum. Just like before, this thing is simply what we're calling the infinity norm of tau over all the steps. What's left over here? Well, this is a sum, and inside that sum, we had this term up at the top that we bounded, and there's where it goes. So again, inequality, where now we're applying the thing right up here. So we are replacing each one of those summands with e to the LT, and then we're just summing it up n times. So once we have made all of these bounds and all these assumptions, once we get to this point, what we end up with is that the global error at the nth time step is then bounded by, well, it's bounded by infinity norm of the local truncation error times a constant, which could actually be pretty large, depending on how large your final time, capital T, is, and how large your Lipschitz constant, capital L, is. However, once we've made all those bounds, what you can say is that this local truncation error term is big O of k. So if I allow k to go to 0, we will get global error at the nth time step going to 0 as we refine our step size. That is our proof of convergence, and it follows from F satisfying that Lipschitz continuity assumption that we mentioned a bit in class. Now here, there are other things that we didn't talk about. We didn't really think about round off errors or any other kinds of practical considerations, but it is an example of how one goes about doing proof of convergence in a simple case. Thanks for joining me on that, and I'll see you in the next video.